Hey students, I thought I'd make a little supplement to kind of add to your ability to solve problems. Let me do the 5 that I mentioned at the end of the lecture for chapter 25. Actually, let me just put there, chapter 25, example problems. And let me do the 5 that were on my list, and we just ran out of time, starting with one very important word that I didn't get a chance to say. I was kind of so busy rushing up the lecture here. But number 36 is a good one because it says, what is the power in diopters of a camera lens that has a 50 millimeter focal length? Okay, so when you make a lens and it has a particular focal length, let me say then you have a less powerful lens. What you mean is it doesn't converge the light so easily, or to put another way, it has a longer focal length. And so I would kind of describe the strength or the power of the lens as the reciprocal of the focal length. Okay, so a short focal length, so something that makes the light converge in a short distance, is really powerful. So small number down here makes a powerful lens. So we like to call the power of it the reciprocal. And if you measure this distance in the units of meters, then you would get for the power in units inverse meters, which is kind of a weird name to say. So we call it a diopter or diopters. And so again, the power is the reciprocal of the focal length, and measuring that in meters would be the power in diopters. And that's where this problem goes, because the problem says, what is the power? So I'm going to put power. And so power is 1 over the focal length. And it says, what is the power in diopters? And it says the focal length is 50 millimeters. So I'm going to go 50 times 10 to the minus 3 to put it in meters. And the symbol we use then for diopters is the D. So grabbing my calculator, I'd go 1 divided by 50 times 10 to the minus 3, which is 20. So this lens would be classified as a power of 20 diopters. Okay? And so that's, like I said, a useful formula, useful discussion, and something that I just didn't get a chance to say. So I thought I'd make sure I covered it right away in an example problem and with our, with an example. And it focused on those units. So there's the units in diopters. All right, let's try number 40. 40 says, how far from the lens must the film of a camera be so that a lens that has a 35 millimeter focal length and is being used to photograph a flower that is 75 centimeters away? So the idea here, and of course I picked this one, object distance, image distance, focal length, which by the way is the power of it, is this relationship that I didn't get a chance to show you any examples, but there's a mathematical relationship between the object distance, the image distance, and the focal length. And then also the magnification. Now, I don't think we'll need magnification for this particular problem, but I might do it anyways, okay? But this is obviously a 35 millimeter camera, so that's why you call it a 35 millimeter camera. It has a lens that has a focal length of 35 millimeters. And so if you were kind of taking a picture, you might have a camera here, kind of an old school camera, where you'd put some film back here. These days, I guess it would be a CCD array. But if you're taking a picture of a flower, okay, they're saying this is 75 centimeters away. And then there would be some focal length, maybe right about there. So the light would come in and converge. The other focal length would be 35 in front. And so it would go straight across. And so the top of the flower would be right there. And the middle of the flower would be here, and the bottom of the flower would be here. And so you would have an image that we'll talk about how much it is reduced. I'm sure it's going to be smaller than 1, unless it's a really tiny flower. But we want to get it on this little electronic CCD array or old school film. But like I said, the magnification is probably less than 1. But it's definitely negative. It's inverted upside down here. Okay? And of course, if you work with these cameras, you turn the barrel here, which moves the lens in and out, because something like this, the focal length is fixed of the lens. And so as you take a picture of something that has a given distance, you're going to want to then adjust the distance from the lens to the film. So this changes, this changes. So you're going to focus, and what you mean is you're going to get a clear image on your film based upon what the object distance is. And so things that are further away will look kind of fuzzy. They're not well in focused. And of course, maybe you've seen that in the movies. A lot of times they'll have, maybe a close-up of somebody's face, and so you've got somebody here and they're kind of looking into the camera, and as they're looking into the camera, maybe there is something in the background, maybe a bush, but you can't really make out the individual leaves. They're kind of blurry because, again, for a set distance of the object, there's a set distance of the image for a set focal length. And so you have this fixed focal length, okay? And that's kind of what we're getting at. So we would take the camera and we would roll this barrel, making the lens move in and out so that the appropriate object distance goes with the appropriate image distance to fit our 35 millimeters. All right, so that hopefully kind of helps a little bit with the lecture part. Let's actually now do the problem, and I would solve it a lot like we did our electronics. Maybe I'll start with 1 over object distance plus 1 over image distance equals 1 over focal length, and point out that I'm trying to find out where the, where should the, how does it say it? How far from the lens be from the film? Okay, so I want to solve for this. And so maybe the first thing to do is to move 1 over the object distance to the other side. And then, of course, the other thing to do is to take the inverse. And I find it best to enter it on my calculator as focal length inverse minus object distance inverse, and then invert the whole thing. And so it looks kind of funny written this way, but this is the best way, I think, to enter it in your calculator. Okay, so the focal length is the 35 millimeters. What was the distance of the flower? So the flower's in centimeters. So I got a judgment call to make here. Should I do everything in millimeters? Should I do everything in centimeters? Should I do everything in meters? The good thing about this equation is as long as you're all in the same units, all inches, all meters, all centimeters, all millimeters, it all works. There is no unit conversion. You just got to be consistent across here. So why don't I be consistent with centimeters? So the focal length is 3.5 centimeters. Yeah, because I say 35 millimeters, so got to change that by 10. Okay, then minus the, 75 away, and then take the inverse. So 3.5 inverse minus 75 inverse, enter. Inverse of that And we're looking at a object distance of about 3.67 centimeters. Which, again, as I probably didn't recognize quite the extra distance here, but from the lens to here would be 35 or 3.5 centimeters. And so there's just an extra 0.17 from the focal length to the film. And my picture shows it a little bit bigger, but the camera could be a little more compact because of it. And of course, if I had even a smaller focal length, this could even be shorter. And so I'm not sure what the focal length is on these new camera phones, but they're really small. It's amazing how well they work, because they still can get focused with such a small focal length. All right, not really asked for this problem, but I thought I would carry it out, is then how big is this image? And so I've got my 3.67 centimeters for the size of my image. And the object, as we said earlier, is the 75. And so let me take that number and divide by 75. And I would say then that the magnification is negative 0.04, and I'll just go 9. That's pretty close to 0.05, which is 1/20th. And let me not forget the negative. So 1/20th, see, this is like a nickel. It takes 20 nickels to make a dollar. But 1/20th then is the size of the image. So, whatever the flower is, maybe the flower and the stem. I'll give it a big flower with a big stem, so it's a big tall rose or something. So if this was 20 inches, well, let me just do 20 centimeters, then the image would be 1 centimeter on the film, and it would be inverted, as we talked about earlier. So that's kind of the meaning there. So again, hopefully that kind of helped you understand a little bit more about these equations and how they work. Let's try another one here. This one looks like it's got multiple parts. It says part A, what is the focal length of a magnifying glass that produces a magnification of 3 when held 5 centimeters from an object, such as looking at a rare coin? And I think I actually have kind of a magnifying glass nearby. Maybe I don't. This could work. But I don't know what you can see there in the camera, but if I was looking here at this 1/20th, I might hold it a distance that is just inside the focal length. In lecture, we call this case number 2, because case number 1 was when it was far away. So you can see if I do this, it's upside down. The negative 120 is upside down. And in fact, it makes the image kind of close here to the screen. And in fact, it looks like it's so close that the autofocus doesn't do a real good job. Let's see if I see if I get closer, which makes it smaller. It puts the image outside of the ability of the camera to focus on it. So this might be a good place to show. Here is case number 1, where the object, which in this case is the words 1/20th, is beyond the focal length, so it's inverted. But if I get close, and they get closer to the focal length, it still is inverted, but it gets bigger. There's a little O there. It gets so big. Now it's at the focal length, all blurry. So now I get inside of the focal length. Maybe I'll get a little closer, because now it's magnified. And so there is negative 1/20th. And so this is what we called case number 2 in the lecture, and we're drawing those pictures in class earlier today here. All right, so that's, I hope, helps a little bit with understanding this problem. And so I would say that the first thing they said was really the magnification. I'll read it again. The question is, what's the focal length of a magnifying glass producing a magnification of 3? And it doesn't say -3, so it's bigger and right side up. And so that would be negative the image distance over the object distance. Okay? And then they said when it is held 5 centimeters from the object. So in other words, they are telling me the object distance also. And so the object distance is 5, and I should watch my units. But again, as long as the units match, it really cancels off. So there are no units to the magnification. It's just 3 times bigger. But they say 5 centimeters. So when I bring the 5 over to here, I get 15 centimeters. And actually, I get a negative 15 centimeters. So again, that's why I said case number 2. Remember, case number 2 is the virtual image. It's right side up, and it is on the virtual side. That's why my camera could focus on it, because when I had the lens here, it was down here, and the camera could focus on something down here. When I had the real image, it was close to the camera's lens, and it was too close for the camera lens to actually bring it into focus. But there's my negative 15. Now, the reason that's important is because then the other equation, 1 over object distance plus 1 over image distance, is 1 over the focal length, which, by the way, is the power. We don't need to solve for power here for this particular problem. But I want to get, I guess, the power first and then take it reciprocal. You might write it this way. If you took object distance and its inverse, and then you took image distance and its inverse, you would get the power. So if you take the inverse of that, you get the focal length. All right, so that's what I'm going to do mathematically. All right, so the object distance. And as I mentioned earlier, I will do everything in centimeters. So I'll get a focal length in centimeters. And by the way, I need to do everything in meters if I'm going to do the power, or at least if I'm going to do the power and report it as diopters, because diopters is in inverse meters. If I want to report the power in inverse centimeters, it doesn't have its own name, but you can just say inverse centimeters. But most of the time we don't do that. Most of the time we report the power of the lens in diopters. So then we need to stick to meters. But for this one, I think I'll just leave things in centimeters. All right, so taking the object distance, which would we say is 5, so 5 reciprocal, and add it to the image distance, which we just said is negative 15 reciprocal, hit enter. Taking the reciprocal of that, we're looking at a focal length of about 7.5 centimeters. And again, those numbers seem to match what we were talking about earlier with the magnifying glass, that you would want to place the object a little closer than the focal length. This is case number 2. So right here, focal length is a little bit closer. See, the focal, I'm sorry, the object distance, which is 5, is a little bit closer than the focal length. We're inside of that. And we're going to make a virtual image. We're case number 2, which is where we make a virtual image. We make it bigger. We make it upright. And when it's virtual, see, negative, virtual. Okay, so there is A. And let me come back here. Let me just read A again. What is the focal length of a magnifying glass that produces a magnification of 3 and is held 5 centimeters from the object, such as looking at a rare coin? B says, calculate the power of this magnifier in diopters. Okay, good. I hinted towards that one. I should have looked ahead and said, hey, they might ask us about power. And so power is the reciprocal of the focal length. But remember, to do it in diopters, we want that distance to be in meters. So instead of me writing 7.5 centimeters, I will write 0.075 meters. So the number is 0.075 reciprocal. And so that's 13.3. And the units would be an inverse meter, which, as I said, is a diopter. And so there's part B. What's the power in diopters? Okay, calculate. All right, C. Discuss how this power compares to those for store-bought, reading glasses. All right, so reading glasses, and you guys are probably too young for reading glasses, and the next chapter is about corrective vision. But kind of a rough picture of a human eye is it has a cornea, and then a lens, and then there's some muscles, and that can squeeze the lens, making it more bowed if needed. And then the eye socket with the retina back here. And this distance is about 2 centimeters. But reading glasses is often needed as you age, because like all parts of your body, your skin in particular, but your lens, it kind of loses its elasticity with age. And what that means is it's not curved enough in order to bring it into focus, especially for things that are close. And so as you get further away, it's kind of easier to focus on things because the lens doesn't have to be squished down as much. And so as you age, this squishiness kind of diminishes. The elasticity of the lens diminishes. And so, and for that matter, the strength of the muscles do too. But as the muscles contract, trying to bow this out, trying to focus on something closer and closer and closer, at some point there's a limit to that. And so there is what we call a near point. And it doesn't matter how old you are, you have a near point. As if you're young, your near point is pretty close. And so generally doctors say if your near point is less than 25 centimeters, you're fine. And so if you've got something close, hold it in your hand and move it closer and closer and closer to your eye. And it just gets harder and harder. And eventually, like this camera, it just can't adjust enough. So it looks like I can read the word pilot here. Kind of here. This is kind of the transition, and then it's kind of blurry here. I mean, I can kind of say it says pilot. But I would say this camera then has a near point of, what is that? 8 centimeters. Okay, so this camera can read something as close as 8 centimeters. So that's its near point. And like I said, the human eye is considered okay as long as your near point is less than 25. But sadly, then, as we age, they get, the lens gets stiffer and the muscles get weaker, and you can't really focus on that. Fortunately, I'm not quite there yet. I do have some reading glasses somewhere. Aha, here's a pair. And they then help because they have a convex shape. And that helps bring the light in. It kind of makes up for this. And these don't actually say what the power is on them. Oh, here they do. The power is 1.5. And so that is telling me power, the inverse of the focal length. And so this would allow me to focus on things closer. In fact, you can probably see it on the camera. It's not that big of a magnifying effect, but it is there. It's nothing like this magnifying glass. Okay, which, well, It says 4 times, but that depends where you hold it. So, and it's actually it's kind of designed to go something like this. It's for kind of studying coins and stuff. I'll open it up a little bit better, but it's designed to put on a piece of paper like that, and so it should make things at the design distance 4 times bigger. Yeah, so there's the F. But that's not necessary here. All right, so anyways, that's kind of this idea of reading glasses. And so most of your reading glasses have a power that is greater than 1, but, and it says less than 4, although I've seen reading glasses that are pretty high, but most people don't need them that high, even at a good age. So, but I have seen them as high as 7. Anyways, this, what did we say, was way stronger than that. So this really becomes a magnifying glass, not a reading glasses. So I don't know if that's so important, but thought I would explain it a little more and kind of use this as a little lecture time. But we're kind of transitioning into the next chapter where we talk in detail about this reading glasses, correcting the lenses, contacts or glasses. And so that's really for tomorrow's lecture in the next chapter. Okay, so hopefully all that was helpful. I said we'd do a few more, so let's see. Let's try a 4th one here. How about number 54? Because the 3 I just did involve lenses, and so let me do 2 involving mirrors. But I also wanted to emphasize, as I said in the lecture, that it's the same basic set of equations, that 1 over the object distance and 1 over the image distance equals 1 over the focal length. And the magnification is negative the image distance over the object distance. And I suppose I should put power is the reciprocal of the frequency. And so there's kind of the 4 equations we're using, whether we use lenses, which is a little more common, or mirrors. So 54 says this. It says some telephoto cameras use a mirror instead of a lens. The radius of curvature of the mirror needed to replace a 800 millimeter focal length is what? Good. And I picked this one because, again, one other thing I wasn't able to say, so just like in number 36, gave me a chance to talk about the power of the lens. This gives me something to say about mirrors that we didn't say about lenses. For lenses, we just said, hey, there is some focal length. And we never really described how you could figure out the focal length. We just said that's what it would be. You could imagine, though, it would have to do with how curved is the first surface when the light enters, how curved is the second surface. And since the bending of light has to do with the speed differential, it would depend upon the n of the lens. I'm going to go ahead and assume that we are roughly in the air for our lens. And so if I wanted to try to figure out the focal length of this lens, it might get pretty complicated, and it is. So your author doesn't go that far. So for lenses, he just says, we'll just give you the focal length, or we will give you the object and image distance and ask you to calculate the focal length. But we won't try to get you to figure out what the focal length is based on the curvature and the speed difference. But for a mirror, it's a little simpler. If the light comes in for a concave mirror and then comes to a focus, so this is the focal length, there is no speed differential. This controlling of the light has to do with reflection, whereas the lens had to do with refraction. So there is no talking about the index. And there's only one curvature. So it must be kind of a simple relationship between the R and the F. And it is. F turns out to be half of R. And I didn't get a chance to say that in the lecture. So I'm going to say it now. And so if you have something simple as a curved lens, the focal length is actually pretty simple. It's half the radius of curvature. And half kind of makes sense, I hope, because if I were to draw the normal here and the normal here, because you know when light comes in, this would be the angle of incidence and this would be the angle of reflection. And you know that the normal on a circle goes right to its center. So this is the center and this is the focal length. And because those two angles are equal, you can see it cuts it in half. And so not necessarily doing a full proof, you can kind of just conceptually see that because the angle is coming in, which would be pointing towards the center of curvature, and the angle of the reflection would double it because angle of incidence equals angle of reflection, you would expect the focal length to be half the radius of curvature. So knowing that, we'll just do kind of a plug and chug here. So let me come back to the question, because it says we're going to use a mirror rather than a lens. And it says, what is the radius of curvature needed to replace a focal length? So if you're saying the focal length is 800 millimeters, so this is some kind of telescopic lens, this would say that if you double the focal length, you get the radius of curvature. So this would be 1600, 8 times 2. I suppose you could move the decimal over 1 and do 160 centimeters, or move it 2 more and go 1.6 meters. And so if you're actually building this mirror, you would, put a grinding stone right here, and you'd put it on a stick that is 1.6 meters long. And then you would just move the grinding stick up and down, and grind that with a radius of 1.6 meters, giving you a focal length of half that, which is 800 millimeters. So that's how the manufacturer would actually build this mirror. Okay? So hopefully that one helped, but that was the idea behind 54. Give me a chance to talk about how you can get the focal length and the radius of curvature. Works really well for mirrors, but we don't have a comparison. Well, let me rephrase that. We do have a comparison for lenses, but it's much more complicated. In fact, I'm going to just write it out. If you have a lens and you would take the material it's made out of and subtract 1, you would then take the radius of the first surface and subtract the radius of the second surface. So it has to do, as I said, with the speed differential, the n, and then the air, and then the 2 radii of curvature, and then you can get the focal length. But your author doesn't even talk about that. We call that the lens maker equation, and that's just a step 1 too far for this class. And so, like I said, we just will give you the focal length of a lens, or maybe have you calculate it from object and image distance, but never calculate it from the radius of curvature or the material it's made out of. All right, one last one, and hopefully this will add to this chapter that was longer than I gave it credit for. Pretty in-depth chapter here. All right, so 57, it says, what is the focal length of a makeup mirror, cosmetic mirror, that produces a magnification of 1.5? So I'll start there with magnification and remind you that it's 1 over image distance over object distance. And they're saying it's 1.5. Now notice it's a positive. And so since a positive magnification only occurs with a concaved mirror, I know that this little cosmetic mirror, it dips in. So it's kind of like the cup of my hand. And a concave mirror performs like this convex lens, a magnifying glass. So it can make things bigger if you're inside the focal length. And it'll make a bigger upright image and further away from you, a virtual image. And so that's what you would want for a cosmetic mirror. You would want to be able to move the mirror, but I don't have a cosmetic mirror here at home. We got some nice ones there at school, but it kind of dips in, and you saw me do that with the red marker in the lecture videos, okay? And it makes things bigger. As long as I was inside, the object is inside of the focal length. All right, so what is the focal length of a makeup mirror that produces a magnification of 1.5 when the person's face, and so the distance the person's face is, so the face will be the object. They're looking into the mirror, they want to see the image of their face, is 12 centimeters, okay? So like we did on a problem for the lenses, if I put this together, I get 1.5 for the magnification. I'll say negative the image distance over 12. And so if I bring 12 over here, 1.5 times would be 12, and another 6 make 18 centimeters. Then with a negative, and that's the image distance. So the image distance would be negative 18. And again, the negative is nice because, again, that would tell me that it's virtual image. That would tell me this is case number 2. This would tell me as it curves in, if this was, if the camera here was the face, and I had my curved mirror, it would make an image on this side and make it away from, make it easier for me to see because it's kind of far away, but it also has magnified it and made it a little bigger here. And so that is the 1.5. And that's what the negative would mean. So, like I said, case number 2. And we're asked to find the focal length. So 1 over object distance plus 1 over image distance is equal to 1 over focal length. So I could write this as the reciprocal of the object distance, the reciprocal of the image distance. Then take the reciprocal of that result, and you get the focal length. Okay, so the object distance is the 12. So 12 reciprocal plus. The image distance, we just said, is a negative 18 reciprocal. Hit enter. Take the reciprocal of that, and we're looking at a focal length of 36, and I did everything in centimeters. And again, that fits to what we have said in other problems and in the lecture. In order to get a positive magnification with a concave mirror or convex lens, you have to have the object closer than the focal length. So our object distance is 12. We're inside of that by quite a bit. It's 36 here. Okay. Now, if I change that to meters and take its reciprocal, so divide by 100, change it to meters, and then take its reciprocal, I get the power in diopters. So the power of this mirror is 2.78 diopters. Okay. Well, maybe that's good enough for a nice supplemental, a good 5 problems with some added information, and hopefully that helps you as you start doing the homework and ultimately preparing for Monday's exam. All right, take care.